A typical shape has two important properties, an area and a perimeter. But can you have a shape that has an area with an infinite perimeter? Might sound crazy and impossible, but such objects actually do exist. Today we'll be celebrating the Christmas season with an easy and classic example of such a shape. Merry Christmas, Happy Holidays everyone, and welcome back to the C-Squared channel. To celebrate the festive season, I'm going to be going away from physics and astronomy for a bit this month, and instead look towards the beauty of a special kind of pattern in mathematics. It is known as the Koch Snowflake, and it is a very simple but interesting fractal pattern with some rather unusual properties. So I'm just going to jump straight to the point, and we're going to go ahead and construct the Koch Snowflake. This is a rather easy construction to do, and it's just to show off what I mean by unusual properties as I've described earlier on. So to begin with, we're going to begin by constructing an equilateral triangle just like so. Now that is not exactly equilateral, but you get the idea. It's a triangle. And we see that each length of this triangle is just 1. The next step is we're going to go ahead and split each side into 3 equal parts. So we're going to take about, let's say, there. See, that's one bit. And another one right there. So you can see we have this. It's not quite split in 3 equal parts, but you get the idea. It's kind of split-ish. Then we're going to do the same with the other parts. So we're going to do it right there. What we do now to construct the snowflake is we're going to draw 3 more equilateral triangles that span from the middle of each side. So we begin doing like this. Like that. That's 1. Now we're going to do the same on this end. That is 2. And once more at the bottom here, we're going to take it to be just like that. Now we have this weird star-like pattern that we're making here. This is the first iteration of the snowflake. So instead of everything being length 1, it's now length 3rd. And that's because we just split everything into 3 parts. And it should be equal. The next step, we're going to go ahead and do the same procedure with every single side. So, just, you're basically just splitting everything into 3 parts once again, but this is with every side now. And now we have made the snowflake pattern. There were a few mistakes when I was drawing it actually. As you can see, a little random line down there, and as well as one right here, because I didn't draw the triangle correctly, but that doesn't matter. The general idea is we've created a whole load of more triangles now. And so what we can infer from this is that, well, basically, we have once again split the lengths of all the sides again. And so instead of having a length 3rd, we now have a length 9th, because all the sides before, when we started off, this big triangle was length 1. These smaller triangles here have length 3rd, and now these even smaller triangles now have length 9th. We can see that there is some iteration processes going on here, since we are repeating this process over and over. The lengths will continue to get smaller and smaller by factors of 3, so the next iteration from this drawing that I made here will give us lengths of 1/27, and so on and so forth. This constant repetition to form a pattern like this is called a fractal pattern, and you can simply go on forever with this. This one fractal in particular is called the Koch Snowflake, since you can see it eventually form something that looks like a snowflake. But this leaves us with an interesting question. What's so weird with this pattern? Well, if you want to continue on with the iterations forever with this fractal, you'll find that you can get a defined value for the area of the snowflake, which makes sense by just simply looking at it. But what happens to its perimeter? What is rather interesting about this fractal pattern is that the perimeter of this shape here actually goes to infinity when you continuously add more iterations onto this. So right now, obviously, you can see there is a perimeter. Just to remind, perimeter is just simply the addition of all the sides. It's the total length of all the sides in the shape. If you were to continue that on forever though, you'll find that these lengths keep getting smaller and smaller and smaller, and it just goes on forever. There is actually no finalized length that you can have. This will just keep going smaller and smaller, and the perimeter will keep on getting larger and larger. And so basically the idea is that the perimeter will go to infinity. So I'm going to draw another snowflake very quickly, just to demonstrate what I mean here. I've drawn another snowflake here. This is the second iteration of it, because you can see you have the central triangle, and then you have the first set of small ones, and then the second set of even smaller ones. Now, we take what we said earlier, with the length being equal to 1. So, of course, for the bigger triangle, we take length of, well, just simply 1. As you can see right there, it's 1. And that is the length of the bigger triangle, the biggest triangle, you could say. Now, when I remember what I said is when you have to split the lengths into 3 equal parts to get the next triangle. So the lengths of the equilateral triangle, after this splitting, you would get it to be equal to 1 over 3, which is right here. Now this is the lengths of these new triangles that I've formed right there. This is the side length of these. And that, as well as all of these actually, this pattern right here I'm drawing out with my finger, all the sides have length of a third. Now if we go once again to the even smaller triangles, these tiny ones here, we will get a length of 1 over 9. And that is because we split these smaller triangles, all the sides that we formed here, into 3 more smaller parts. And we just take the middle bits. So we are left with these small little areas now, and all of these have a side length of 1 over 9. Now there is a pattern here. You might have realized it by now, but there is in fact a pattern. The pattern is that you start from 1 and you keep dividing this length by 3 each time after every iteration. So the mathematical version of this is simply this expression right here. This is the length of each side after every iteration. So you can see Sn is just the length of the side after n iterations, and this is how much the length would be. So to quickly test this out, if we want to get the length of just that big triangle there, we take it to be the 0th iteration, so it's basically the starting point. So if n is equal to 0, then you have 1 over 3 to the power of 0, and anything to the power of 0 is equal to 1, except for 0. So you're basically dividing by 1. So 1 over 1, you're just left with 1. So, and that was the starting length of the big triangle, as we have already derived. Now, if we were to take n equal to 1 for the first iteration, you would have n equal to 1 down there, so it would be 1 over 3, which is Sn. And 1 over 3, of course, we found is the length of the triangle after the first iteration. And then once again, you could do it again with n equal 2, and you'll find that is equal to 1 over 9. And n equals 3 would be 1 over 27, and then so on and so forth. So there is a pattern, a recurrence pattern going on here. So what matters here is the number of sides you actually have. So the first set, you have 3 sides, easy enough. Next set, you have 4 triangles, so you correspond to 12 sides. Finally, you have 10 triangles, and that corresponds to 48 sides. So we can get another mathematical expression for this, which is written right here. So the number of sides is equal to 3 times 4 to the power of n. So this will give you the number of sides after any iteration in this fractal pattern. Now, if you want to get the perimeter, we simply multiply the number of sides by the lengths of each side. That's how you get the perimeter of the shape in this one particular case. And you get something rather interesting if you try to calculate that. So this is the value of the perimeter at any iteration. 3 times 4 over 3 to the power of n. When you increase the iterations, when you keep going up more iterations, the perimeter should actually go on to infinity. That is indeed what happens. And you can clearly see as you continuously increase the iterations, you would have, well, the lengths get shorter by 3 times, but the number of sides you get increased by 4 times. And this reaches where you basically have no upper limit to this. This will just continuously go on forever. You can even plot it out if you want, this plot right here, and you'll find that this will correspond to some kind of exponential graph just going off to infinity. And this basically implies that the Koch Snowflake or at an infinite iteration, will have an infinite perimeter. So what about the area of this shape, or this kind of fractal pattern here? Well, the area actually has a slightly different behavior. The maths behind this one is actually quite a lot to deal with, so I'm not going to go into the maths of it, but the general idea is that the area actually does have a defined value as you continuously, increase up to infinity. And I find that rather interesting. So if we start with the central triangle here, this big middle one here, and we'll call the area of that A, so that's just a typical area. And what we find is that every iteration that you add on to, so all these new triangles you keep adding on forever to infinity, will actually be contributing less and less to this initial starting area. And that is very intriguing, because this means that these smaller triangles here will be getting less and less area each time. It's going to keep, it will keep adding on, of course, it will just continuously add on, but the contribution will be less and less and less. And so what you get in the end is the final result. If you have an infinite amount of iterations, you'd find that this will actually contribute to 1.6 times more than this starting value of A for any cofractal. Now, of course, the maths of that, again, I'm not going to go into detail, but I find that to be a very interesting property. And I find it extremely bizarre how something like this can have a well-defined area at an infinite iteration, but the perimeter will just keep going on forever. It seems to make no sense, but that is how fractal patterns, just like the Koch Snowflake, actually work. This type of weird property is not only observed in the Koch Snowflake, but in fact you can find this across a huge range of fractal patterns. The most famous of these is the Mandelbrot set, but others include the Julia set and Gabriel's horn as well, where instead of having an infinite perimeter with a finite area, you'll have an infinite surface area but a finite volume. So I hope you guys all learned something about fractals today. If you enjoyed this video, be sure to subscribe and share the video around to help the channel grow. That would be very much appreciated. Thank you all so much for watching this video, and I'll see you all in the next one.